If I asked you what happened before the universe began, what would be the first thing that came to mind? You would probably imagine a dark, empty space, right? The thing is, according to our current best understanding of physics, there may not have actually been a before to imagine at all. This is because time itself may not have existed yet. That's not poetic language. See, time and space are woven together in what physicists call space-time. You've probably heard of the Big Bang before. Well, it didn't get that name from describing an explosion in space. Rather, it describes the expansion of space itself. And if space is expanding, then that means time expands with it. So asking what happened before the Big Bang may be like asking what's north of the North Pole. The question assumes a direction that may not exist. According to the standard cosmological model, time as we measure it begins at the Big Bang, about 13.8 billion years ago. How do we get that number? Because when we look out into space, something surprising happens. Nearly every distant galaxy we observe is moving away from us, and not just drifting, receding. The farther away a galaxy is, the faster it appears to be moving away. This is because space itself is expanding, stretching between galaxies, carrying them apart like raisins separating in rising bread dough. If everything is moving away from everything else today, then that means we can mathematically reverse that motion. We can keep rewinding. And as we do, the universe gets closer until we reach a state where our current laws of physics break down. And that's important. When we say the universe began, we don't mean we have a complete description of that first moment. We mean that our equations can trace the universe back to an extremely hot, dense early state, and then they stop working. There is a wall, not necessarily in reality itself, but in our understanding of it, and that wall is humbling, because it means the beginning of time is not just a dramatic idea, it's a boundary of human knowledge. But here's the key, that boundary is incredibly thin. While we can't describe the exact instant of the beginning, we can describe what happened immediately after, when the universe was already expanding, already evolving, and our equations begin to work again. And what happened in that first tiny fraction of a second shaped everything that followed. Let's go back to not even a minute after the Big Bang, not even a second. Let's zoom to a fraction of a second. In the tiniest sliver of time imaginable, something extraordinary appears to have occurred. Most scientists believe the universe went through a phase called cosmic inflation. Don't think of this in the Saw way as a balloon slowly inflating with air. This inflation refers to an expansion that was unimaginably fast. According to the theory, in less than a trillionth of a trillionth of a trillionth of a second, the universe expanded from smaller than an atom to something macroscopic, meaning it's large enough to measure. That's like a grain of sand suddenly swelling to the size of a planet before you could even blink. It grew faster than the speed of light, which you may have heard is impossible, but physics only applies that limit to objects moving through space. During inflation, it wasn't objects moving, it was space itself expanding, increasing the distance between points faster than light could travel across it. If this is sounding a bit too abstract, try imagining that you're drawing two dots on a rubber sheet. If you stretch the sheet, the dots move apart, not because they're traveling, but because the surface between them is growing. That's what inflation proposes happened to the entire universe. Galaxies weren't blasting outward through empty space. Space itself was being stretched, carrying everything with it. This cosmic inflation explains something that once confused scientists deeply. When we look out at the universe in every direction, something surprising shows up. The temperature of space, measured through the cosmic microwave background, is almost exactly the same everywhere. Not roughly the same, nearly identical down to tiny fractions of a degree. And at first, that might not sound strange. But here's the problem. Light has a speed limit. Nothing travels faster than light through space. And when we calculate how long the universe had existed before that light was released, there simply wasn't enough time for distant regions to talk to each other. Imagine two ovens on opposite sides of the country that have never been connected. No shared wiring, no shared air, no shared heat. And yet somehow, when you measure them, they are set to exactly the same temperature, down to a millionth of a degree. You would immediately suspect they were once connected. That's the puzzle. Regions on opposite sides of the observable universe are so far apart that, under normal expansion, they never should have been able to exchange energy or information. And yet, they look almost perfectly uniform. Inflation offers a solution. It suggests that before the rapid stretching, the entire observable universe was compressed into a much smaller region, small enough for everything to reach the same temperature. Then inflation happened, and space stretched enormously and extremely fast, pulling those once neighboring regions so far apart that light simply hasn't had time to cross the distance between them. So the uniformity we see today isn't mysterious coordination across vast distances. It's a memory of when everything was close together. But inflation didn't just stretch space, it stretched tiny imperfections down to the smallest possible scales of reality. In this quantum realm, which operates on a level far smaller than atoms, the universe is never perfectly smooth. According to quantum physics, energy naturally flickers. Even in what we think of as empty space, there are microscopic ripples and irregularities. Normally, these fluctuations are unimaginably small. They appear and disappear constantly, like tiny wrinkles forming and vanishing on the surface of water. But during inflation, space expanded so violently and so quickly that those microscopic ripples were stretched to cosmic size, and those tiny wrinkles became the seeds of galaxies. Let that sink in. The reason galaxies exist, the reason stars formed, the reason planets, oceans, and you exist may trace back to microscopic flickers in the earliest fraction of a second. Even though the evidence strongly supports inflation, we still don't know what caused it. If it is true, then that means structure in the universe began with randomness at the quantum level, a concept that can be both unsettling and beautiful. Out of quantum anomalies came the blueprint for galaxies. When it stopped, all of that rapid expansion left the universe in a very different state. Space was now vastly larger, but it was still filled with extraordinary energy. In fact, when inflation ended, that stored energy was released back into space, heating it to extreme temperatures. So the universe didn't suddenly become calm or empty. It became extremely hot. But now, expansion continued at a steadier pace, no longer exploding outward exponentially, and this slower rate of expansion allowed cooling to finally take place. In the early moments after inflation, the universe was not made of stars or planets. It wasn't even made of atoms yet. Now, atoms are the basic building blocks of everything around you, and they are made up of a dense nucleus made of smaller particles like protons, with even smaller particles, electrons, orbiting around them. In the early universe, it was far too hot for this structure to even exist, and instead of stable atoms, there was a chaotic mixture of free electrons and atomic nuclei moving rapidly in every direction. When something is hot, it radiates energy. Think about how heated metal begins to glow, or how the surface of the sun shines. Heat produces light, so this extreme heat in the universe meant the universe was filled with intense radiation, or extremely energetic light. Every time an electron tried to join a nucleus to form an atom, that energetic light would slam into it and knock it free again. Imagine trying to build a house in the middle of a hurricane. Every time you place a brick, the wind just rips it away. That was the scene of the early universe, but as space continued to expand, the universe continued to cool. Eventually, Over hundreds of thousands of years, temperatures dropped enough for protons and electrons to finally combine, forming stable hydrogen atoms and helium atoms. This event is called recombination, even though it was technically the first time they combined. When atoms finally formed, something profound happened. Light was finally free to travel. Before this moment, the universe wasn't transparent. It was more like a thick, glowing fog. Photons, the particles of light, were constantly colliding with free electrons. Every direction was crowded, so light couldn't go very far without hitting something. But once electrons locked into atoms, that constant scattering stopped. Suddenly, light could move freely across space. The fog lifted, and the universe became transparent. The fascinating part is that very light, released when the universe first became transparent, is still traveling today, and we can detect it. It's called the cosmic microwave background. You can think of it as the oldest photograph we have of the universe. When scientists map it, they're seeing the universe as it was about 380,000 years old, which, compared to 13.8 billion years, is basically infancy. But here's where it gets even more interesting. That ancient light isn't perfectly smooth. If the early universe had been completely uniform, the exact same density and temperature everywhere, then nothing would have ever formed. Matter would have remained evenly spread out forever. No clumps, no stars, no galaxies. Perfect smoothness would mean perfect emptiness. But when scientists look closely at the cosmic microwave background, they see tiny temperature differences, slight hot spots and cold spots with differences so small they're measured in fractions of a degree. But these variations aren't just random occurrences. They trace all the way back to the microscopic irregularities we talked about earlier, the tiny quantum fluctuations that were stretched to cosmic size during inflation. In other words, the same small ripples in energy from the universe's first fraction of a second were now visible in this ancient light, and those slight differences mattered. The slightly warmer regions were a bit denser, which is important because gravity pulls more strongly where there is more mass. So over millions and then billions of years, those tiny overdense regions continued to pull in more material, and the slightly emptier regions continued to lose more. Little differences became larger ones, and those amplified differences became the starting points for everything that followed. Stars, galaxies, clusters, the entire cosmic web. Ironically, after recombination allowed light to finally travel, the universe entered what astronomers sometimes call the cosmic dark ages. There were no stars yet, no galaxies, just vast clouds of hydrogen and helium drifting in expanding space. But gravity was quietly at work. Those tiny fluctuations we mentioned earlier, the slight overdensities in matter, meant some regions had slightly more mass than others, and gravity pulls mass toward mass. So slowly, over millions of years, gas began clumping together. Think of it like mist condensing into droplets. As gas clouds grew denser, gravity pulled harder and harder until the clouds began collapsing inward. And this is where everything changed. When gravity pulls matter inward, particles progressively speed up as they fall toward the center. As they crowd together, they collide more and more often, and these collisions increase temperature. The deeper the collapse, the hotter the core becomes, and eventually temperatures rose high enough for nuclear fusion to begin. You see, under normal conditions, protons, the positively charged particles inside the nucleus of atoms, repel each other. They don't want to stick together, but at high enough temperatures they move fast enough to overcome their natural electrical repulsion. This is nuclear fusion, when atomic nuclei combine to form new, heavier elements. An element is determined by the number of protons in the nucleus, so when hydrogen atoms, containing one proton, fuse together, they form helium atoms with two protons. When this happens, a tiny amount of mass is converted directly into energy. According to Einstein's famous equation, energy equals mass times the speed of light squared. According to this, nuclear fusion releases enormous amounts of energy outward in the form of light and heat. So as gravity pulled gas clouds inward, fusion released energy outward as radiation. And when those two forces balanced, something spectacular happened. A star was born. When the first stars ignited, the universe lit up and the cosmic dark ages were over. But these first stars were likely very different from many stars we see today. The early universe contained almost nothing but hydrogen and helium. There were no heavier elements yet, and without these cooling elements, early gas clouds tended to form much larger stars, and larger stars behave differently. The more massive a star is, the stronger its gravity, and stronger gravity compresses the core more intensely, raising the temperature. This higher temperature means fusion reactions occur faster, and faster fusion means the star burns through its fuel more quickly. So the earliest stars were likely extremely massive, extremely bright, and extremely short-lived. They burned fast and they died young, but during their brief lives, they transformed the chemistry of the universe. Inside their cores, nuclear fusion took place, performing alchemy on a cosmic scale. Hydrogen fused into helium, helium fused into carbon, carbon into oxygen. In the most massive stars, fusion continued all the way up to iron, which marked a turning point. This is because fusing iron does not release energy, it absorbs it. So once a massive star builds up an iron core, fusion can no longer support it against gravity. Gravity suddenly wins. The core collapses in a fraction of a second, and the star explodes as a supernova. In those violent explosions, temperatures and pressures become so extreme that elements heavier than iron are forged, such as gold, uranium, and many others. Many of the atoms that make up the world around you were created in those explosions, and then they were scattered, blasted outward into space, mixing with the surrounding gas. Stars continued to form, but these newer generations didn't form from pure hydrogen and helium anymore. The gas now contained new, heavier elements like carbon, oxygen, and iron, and that changed everything. Gravity doesn't just pull gas into stars. When a new star is being formed, the collapsing gas doesn't just fall straight inward. It spins, and when the new star is formed, the gas surrounding it, still spinning, flattens into a rotating disk. Gravity holds that disk in place. And with carbon, silicon, iron, and other elements present, that disk now contains solid particles. Inside of it, these tiny grains begin sticking together. Dust becomes pebbles, pebbles become rocks, and rocks collide and merge into larger bodies. Eventually, gravity assembles those fragments into entire planetary systems. Planets, gas giants, moons, asteroids, and comets, all assembled from the recycled material of earlier stars. So gravity did more than ignite stars. It organized what surrounded them. It turned enriched debris into structured systems. It shaped rotating disks into solar systems. It transformed stellar ashes into new worlds. But gravity was operating on even larger scales at the same time, because stars were not forming alone in empty space. They were forming inside vast regions of gravitational influence that extended far beyond any single solar system. The same force that collapsed gas into a star, the same force that gathered dust into planets, was also assembling something much bigger. But before we get there, consider this. Everything we've described so far, inflation, the CMB, star formation, everything has been supported by layers of observational evidence. All of these telescopes and satellites and particle physics experiments, and yet we are still only describing about 5% of what the universe appears to be made of. The rest, that's where the mystery deepens. We just saw how gravity ignited stars and shaped planetary systems from enriched debris, but those systems were never floating alone. They were forming inside something larger, vast regions of gravitational influence that had been taking shape since the early universe. Long before the first stars ever ignited, gravity had already begun assembling an invisible framework. Astronomers call it dark matter, and to understand it, we have to look at what seeing actually means. Everything you've ever seen, from a distant star to your own hand, is visible because of how it interacts with light. Light is a form of energy that travels through space, and when it encounters ordinary matter, only a few simple things can happen. It can bounce off a surface. This is reflection, and it's what allows your eyes to detect objects. It can be absorbed, where the energy is taken in and often converted into heat. Or it can pass through and then be re-emitted, what we call radiation, where matter briefly holds that energy before releasing it again. Every visible object follows these rules. If something interacts with light, we can, in principle, see it. But what if something doesn't? That's where dark matter enters the story. It doesn't reflect light, it doesn't absorb it, and it doesn't emit it. As far as we can tell, it is completely invisible, and yet its gravitational influence is unmistakable. When scientists began measuring how galaxies rotate, they discovered something that shouldn't be possible. Stars at the outer edges were moving far faster than what could be explained with gravity from visible matter alone. At those speeds, galaxies should have torn themselves apart, but they didn't. So the logical conclusion was that something unseen was there, adding extra gravity, holding everything together. That something outweighs all visible matter by roughly 5 to 1. And in the early universe, it changed everything. While normal matter was still interacting with radiation, bouncing photons around in that dense glowing fog we talked about earlier, dark matter was unaffected. It didn't interact with light at all, which meant it could begin collapsing under gravity much earlier. It gathered quietly, gradually forming dense, invisible regions, what we call halos. Think of them like valleys carved into the fabric of space by gravity. Deep gravitational wells waiting to pull matter inward. When the universe finally cooled enough for light to travel freely, ordinary matter was released from that fog, and it fell into them. Gas streamed inward. Hydrogen and helium flowed along vast filaments, like rivers feeding into basins. Inside those dark matter halos, the first galaxies began to take shape. At first, these proto-galaxies were small and chaotic, just loose clouds of gas and young stars held together by gravity. But over time, gravity pulls things toward other mass, so over millions and billions of years, these systems began to merge, but these galaxies didn't collide like solid objects. They passed through each other like overlapping clouds. Their gravity mixed everything, stretching orbits, pulling stars into new paths, and compressing gas. Small galaxies became larger ones. Then the larger ones merged again. Over time, these formations began to flatten into disks. Spiral arms emerged, and the central regions grew more and more dense, until eventually, something extraordinary appeared at the heart of almost every galaxy. Black holes, so massive that they are millions, sometimes even billions of times, more massive than our sun. These actually formed quicker than expected, and how they did so is still one of the great mysteries of cosmology. Some may have grown from the first massive stars. Others may have formed from the direct collapse of enormous gas clouds, but whatever their origin, they now anchor galaxies, shaping their motion from the center outward. And when we zoom out even further, something even more astonishing appears. These galaxies aren't spread randomly through space. They trace out a pattern, filaments stretching across hundreds of millions of light years, dense nodes where clusters gather, and enormous empty voids in between, what we call the cosmic web. By mapping the positions of millions of galaxies, astronomers can see this structure directly. Large sky surveys reveal the same pattern again and again: strands, clusters, and empty gaps. This structure traces all the way back to the earliest moments of the universe, back to the tiny quantum fluctuations that stretched across space during inflation. The smallest ripples became the largest structures. Gravity didn't just form stars. It didn't just build galaxies. It sculpted the architecture of the entire universe. But now we step back even further, because once we understand why galaxies exist, a deeper question emerges. If gravity is constantly pulling matter together, why is everything moving apart? In the early 20th century, astronomers began studying the light from distant galaxies more carefully. They noticed something subtle. The light was shifted. When an object moves toward you, its light compresses into shorter wavelengths, shifting toward blue. When it moves away, the light stretches into longer wavelengths, shifting toward red. This effect is called redshift, and nearly every distant galaxy showed it. Not just a few, almost all of them. Then came the breakthrough. In 1929, Edwin Hubble discovered that the farther away a galaxy is, the more its light is redshifted. In other words, the farther it is, the faster it's moving away. This wasn't just motion through space, it was something deeper. Space itself was expanding. A helpful way to imagine this is with a balloon. If you draw dots on its surface and inflate it, every dot moves away from every other dot, not because they're traveling across the surface, but because the surface itself is stretching. That's our universe. There is no central point everything is moving away from. From any galaxy in any direction, everything appears to be receding. Expansion is built into space-time itself, and for a long time, scientists assumed something intuitive. If gravity pulls matter together, then over time, expansion should slow down. It might never fully stop, but it should decelerate. But in the late 1990s, observations revealed something completely unexpected. Expansion isn't slowing, it's accelerating. Galaxies are moving apart faster today than they were billions of years ago. Something is pushing the universe outward. We call it dark energy, not because we understand what it is, but because we can measure what it does. Dark energy appears to make up about 70% of the universe, and unlike matter, which clumps together under gravity, dark energy behaves like a property of space itself. As space expands, more of it appears, and the expansion accelerates further. Gravity pulls matter inward, building structure, while dark energy pushes space outward, stretching everything apart. And now, the universe exists in a kind of balance between these two effects. Locally, gravity wins, forming stars, galaxies, and clusters, but on the largest scales, dark energy dominates, driving everything apart. The universe is simultaneously building structure and dissolving connection. And that leads us to the final question. If expansion is accelerating, what happens next? Today, we estimate the universe to be about 13.8 billion years old. And because space itself has been expanding, the observable universe spans roughly 93 billion light-years across. And when we take a full inventory of everything that exists, something surprising appears. Everything you can see, every star, every galaxy, every atom in your body, makes up only about 5% of the universe. Roughly 27% is dark matter, and about 68% is dark energy. In other words, the universe we experience is just a thin, visible layer resting on something far deeper, something beyond our comprehension. And yet, its future depends on that unseen majority. If dark energy remains constant, expansion will continue forever. Over trillions of years, distant galaxies will move so far away that their light can no longer reach us. The night sky will slowly grow darker, stars will burn out, galaxies will fade, energy will spread thinner and thinner. Eventually, the universe would approach what physicists call heat death, a state where no usable energy remains to sustain structure or life. If dark energy grows stronger, a more extreme outcome is possible. The Big Rip. Expansion could become so powerful that space would be pulled apart at every scale. It would tear apart galaxies, then solar systems, then planets, and eventually even atoms themselves. And if instead dark energy were to weaken, then gravity would take over again. Expansion would slow, then stop, and then reverse. Galaxies would fall back together, temperatures would rise, and the universe could collapse in a big crunch, perhaps even beginning a new cycle. We don't yet know which path awaits, but here's what we do know. From a quantum fluctuation smaller than an atom, to gravity forging stars and galaxies, to dark energy shaping cosmic destiny, the same physical laws have governed every stage. Structure became stars, stars became chemistry, chemistry became biology, and biology became us. The more we learn, the more we realize how much remains to be discovered, and how much of reality still waits to be understood. Thanks for watching, and be sure to like and subscribe if you'd like to continue this exploration of reality together and bridge the gap between the visible and the infinite.